first, what happens, and then the black wins, right? That's what we want to analyze.
Well, I get it.
There's a left side move, there's a right side move, and there's a center move. But don't worry about it for now. All right, so this warm-up. What new information can we add? Let's start with Decker.
Okay, I don't know if this is
That's fine. We want conjectures.
Okay, so I was trying to get the sides of the three triangles of the sides.
Okay, these guys,
Or no, I mean the square. What's kind of, I don't know how to describe.
the boxes.
Yeah.
All right, we're trying to get the box.
So 27. So the area's in the middle, right? 27.
Yeah, the area of this is 27.
So 9 and 3. 9 times 3 is the area of that. And
The sides, you mean?
Yeah, yeah.
How do you know it's 9 and 3 and not something else? It could be root 27 or root 27. It could be a square.
I don't know.
It could be 2 and 27 halves.
Well, I don't. Can I show you what I
If it's whole numbers, we can assume 9 and 3.
But since like all the triangles are like
Similar.
similar, so they don't really have the same size necessarily.
Right.
And so.
All right, so I think what you did is you assumed that this was 9 and that was 3.
No, that no. Well,
Or vice versa,
yeah.
right? Okay, so that's fine, right? If you want to solve a similar problem, right? Obviously, this problem, we don't know that. That's 9 and 3. Could be the other way around. Also could not be whole numbers.
I have a reason why I put them in the way.
Why does it have to be 9 and 3?
Well, I don't have a specific reason why it's 9 and 3. Like I don't know. I have.
Okay. So what I'm saying is that it could be 9 and 3 here, or it could be 9 and 3 here. Or what if it doesn't have to be whole numbers, right? The box doesn't necessarily have to be whole numbers, right? No, what do you got?
Like you were saying about the hypotenuse leg or whatever.
Mhm.
If we imagine that, or if we said that the boxes were squares, we don't know that, right?
We don't know that, but if we did, right?
Then we could get the hypotenuse using SAP or like second edition postulate for the bottom of the. I don't know. I'm not
So you'd add up all the hypotenuses, right?
Yeah.
Is that what you're saying?
And then you could get the area.
Right.
Just
So Noah's game plan, how we get there, not sure, but the game plan is if we can get the hypotenuses here, here, and here, we can add them up, and then we get the side of the square. How do we get those hypotenuses?
you square the areas vertical. That they don't have to be like perfect whole numbers. I don't think. Wait. hold
So
on.
are you saying if we knew the dimensions here, we could get this by Pythag, right?
Yeah, if you knew like the. Oh wait, we don't know the bottom one.
Right, and this isn't 27 in height. Remember, that's the area of
No,
this
yeah,
square.
no, but if you root it, then you would have.
Ooh, got it. Okay, so Noah's saying that if we knew these were squares, then this would be root 27, this length right here, and this would be root 12, and that would be root 3.
Yeah.
Does that make sense? Because root 3 times root 3 gets you 3, root 12 times root 12 gets you 12, root 27 times root 27, right? When you square a root, you get the number inside. So this would be root 27. And if we knew this length, then we could do Pythag to figure out this and do the same for all the rest. And that's true, but unfortunately we don't know that one. If there's a way to get it, then that'd be great. Yeah, good thought.
We can get that because we can assume that they're squares. It'll be root 27 for all of the sides. And then that means that root 27 for that square is going to be the length of the middle right triangle on the right side is going to be that bottom length is going to be root 27 minus root 12.
Got it. Okay. So if we assume they're squares, again, this is not solving the problem, but it's solving a similar problem, then this would be root 27 here. Does everybody get that Noah brought up? Right? Root 27 by root 27 gets you 27 area, right? So Zayden's logic is, well, if that's a square and this is a square, that's root 12. The whole thing's root 27. By segment addition postulate, I can do root 27 minus root 12, and I get this. So I'm going to write on a separate sheet of paper because we're solving a different problem, technically. Where are my copies? Okay. So what he's saying is, look, if these are squares, this whole thing is root 27, and this whole thing is root 12, which means this length right here, which I'll do in purple, would be root 27 minus root 12, which is not a pretty number, but it is accurately what it is, right? It'll be some decimal. Both of those are not perfect roots. And now we have this, and we've got this as root 12. So we've got these two legs, we can figure out the hypotenuse. And if we've got this hypotenuse, Maybe there's a way to get these guys. Zayden, what else do you have to say?
Since we know that the side length for the bottom right triangle on the right side, that side length is going to be root 27.
Mm-hmm.
And by similar triangles, we could find the one in the bottom by using the same ratio as the one in the middle.
Sure.
And we can do that for the top one as well.
So if we figure out these two in their ratio, right, it should be the same ratio here since these triangles are similar. So whatever root 12 compares to root 27 minus root 12 will be the same way that root 27 compares to its side. Okay? That's the idea. So first let's find the hypotenuse here. Again, this is assuming these are squares. We're not solving the problem, but we're solving a quote-unquote easier problem, right? At least a problem that we have a road, to solve. So the hypotenuse here is going to be root 12 squared, right? Plus root 27 minus root 12 squared, and that's going to be the hypotenuse. So that means we root it, right, for Pythag. So what is root 12 squared?
3.4.
I don't want to, nope, what's root 12 squared?
Oh, root 12 squared is
The square number means times it by itself, right? What's root 12 times root 12?
12.
12, right? Right? Squares and square roots cancel. That's the whole point. So that's 12. Now this, it's not just going to be root 27 minus 12. And the reason for that is because we have two terms here, right? We need to multiply it by itself. So if we were to do that, what we have is this. Woo! We have to distribute that, right? You guys remember FOIL, right? Something like that. We're going to distribute the negative 12 rooted, and we're going to distribute the 27 rooted. That's all it is. That's all FOIL is. It's just distributing everything. This gets distributed, then that gets distributed. Okay? So what do we get? Let's distribute the negative 12, root negative 12 first. So here and here, we get negative root 12 times root 27. Here and here, negative and negative makes a good, and root 12 times root 12 is 12. So we just have 12. All right, now let's distribute the root 27. What's root 27 times root 27? 27. And what's root 27 times negative root 12? It's all this. Yuck. What do you notice? We have two of these, right? So can't we write that simply as 2 root 12 times root 27s plus 12. And then 12 plus 27, what's that going to get us? So we have 39 minus 2 root 12 root 27. Now some of you guys are like, man, can we combine those somehow?
Wait.
Let's find out. Let's go with roots we do know. What's root 9 and root 16? Root 9 is what? 3. What's root 16? So that's 12. Now, a lot of you guys are thinking, can I just multiply those? All right, what's 9 times 16? What's 9 times 10?
90.
What's 9 times 6?
54.
So it's 144 under the root. Does that give us 12?
No.
Yes.
Wait, yeah.
Yeah, so you can do that, right? I just showed that, look, I know what this should equal, right? Root 9 is 3, root 16 is 4, when I multiply them together, I should get 12. Can I just combine them and keep them under the root? I can, because look, that's also 12. I didn't break math. So I went with what I knew to figure out a problem I didn't know, right? Again, when we are confronted with something we're not sure of how to solve, make a similar related problem, right? I didn't know if you can combine those. I didn't memorize algebra. I just try it out and see if it works. Do it with something you do know. I know that should be 12. So when I do this, does it still keep 12? And if it does, then I must not have broken math. So I can write this as 39 minus 2 times, we need 12 times 27. How would you do that?
27 times 10.
27 times 10, 270. And 27 times 2. What's 27 times 2? 54. So we have 270 plus 54, 324. All right, so that's the hypotenuse. So this hypotenuse right here is 39 minus 2 root 324. All right, let's pretend that's about 39. It's not. Well, let's pretend it's about 39. If this is 39, this side has to be longer than 39. Let's pretend it's 40, right? If this is 39, doesn't the whole thing have to be longer than 39? Right? So let's pretend the whole thing's 40. Okay? We can get a rough estimate. 40 squared is what we get, right? So this is a very rough estimate. We're extrapolating this all out, right? But we're saying, look, we got a ballpark figure here. That's a load of nonsense, right? It looks awful. But at least we've got some idea, right? Does anybody know what the root of 324 is approximately? I think it's about 17-ish. So we have got 39 minus 17. That's going to be about 22. So this is 22. Maybe this is 11. Maybe this is 33, right? We're getting in the range of like 60 or 70 across here. So we've got 70 squared to be the area, somewhere around there. That's just an estimate. That's assuming these are squares. But yeah. What did you say, Zayden?
You forgot to double the 17.
I forgot to double the 17. Oh, yeah, and then double it, right? So we double it and get 34, so it's about 5. Ooh, that'd be interesting, right? About 5, and then we get about 4, about 3. I don't know, right? Interesting, interesting. Okay, so. And root 12 is about 4. This is about 3, yeah. So we can take this and find out the ratio and find out what this hypotenuse is, right? How do you want to do that? Looks like we got root 12. What side does it relate to? On the other triangle, on this triangle here. All right, so the question is, when they relate, does it go on the bottom or does it go here? Remember when we did it, we would match up letters from the first triangle and we put it at the top? Right? And the first triangle's parts would always go on the top. Do you guys remember that? Like if I have two triangles that are similar, when we use CSP, didn't we do something like AB and DE go together and BC and EF go together, right? So see how the first triangle's parts go on the top? So root 12 and all this stuff would go on the top if we were to write them all out, right? So this guy must go on the bottom. So root 12 is to root 27, the same way that 39 minus 2 root 324 is to, we don't know, x. That bottom line, or that hypotenuse. Now, we could have done it as well. Root 12 is to this, as root 27 is to this bottom. But I figure why not just go and get the hypotenuse? All right. I'm going to write this out bigger. I'm going to try and find this hypotenuse. We'll call it a day, and I'll leave you at that, okay? So, we've got root 12 over root 27. And that equals, we don't know, the hypotenuse we're looking for. And then we got this big pile of junk. 39 minus 2 root 324. All right. So we want to get x on its own. Is it easier to solve for x on the bottom or if x is on top? Right? If I gave you an equation like this, a half equals x over 4, or if I gave you half equals 4 over x, which one would be easier to solve for, right? This one, right? Times by 4 and you're done. Can't we just split both? As long as you do it to both sides, it's algebra, not child abuse, right? That holds up in a court of law. Exactly. You ever played Phoenix Wright, the DS game? Objection! I've always wanted to say that. All right. That's an easier problem to solve. It's not easy, but it's easier. How do we get x on its own? Right? If there was a 2 under here, just a 2, you multiply by 2, right? We're going to multiply by all of this. You need to wrap it in parentheses because there's 2 ideas here, right? There's a minus sign separating 2 different terms. So what we end up getting is this. 39 minus 2 root 324 times root 12 over, root 27 over root 12 equals x. Now, that's the hypotenuse. Could I do math and distribute stuff and move things? Yeah, sure, right? But like, that's it. If you're to type it in a calculator, you get an answer. You want to simplify? Good, do it, right? It'll probably make your math easier when you have to go and get this guy. I don't know. But those are the hypotenuses. So notice that that number is the same as this number. Let me write that down. This right here is 39 minus 2 root 324 times root 27 over root 12. Right? Okay, so notice that they both have the same part here. But this one's just times root 27 over root 12. So it's like if this were 3 and that were 3 times 2, right? It's double. The relationship is here. That's how they're related. Root 27 over root 12. So that's the relationship between these two triangles. This one is root 27 over root 12 bigger, times bigger. What's root 27 approximately? What's the root you do know that's close to 27? Right? Root 25, you know. So it's approximately 5. What's root 12 approximately? 3 or 4. It's like right in the middle, right? So it's like 5/3 or 5/4. That's interesting. 5, 4, and 3 are all right triangle numbers, right? 3, 4, 5. So we're on to something. You can figure out this guy and then add them all up and you've got your length. And then square them. Get your area.
Yeah, but we don't know their squares.
We don't know their squares. But if they were squares, we could solve it. Now, what did we learn from this? Well, one, we learned about this, right? We're allowed to combine those and make 144. Did we solve the problem that they wanted to solve? Oh, no. Oh, God, no. No. But we did learn something. Always try to learn something, right? We also learned that if we just knew the lengths of these squares, we'd be able to find the different lengths of the triangles, right? Now, hopefully, there'll be nicer numbers than this. But that's what we need to find out. How do we get the lengths of these rectangles when we assume the problem isn't that they're all squares? Here's something I thought about the other night. Because again, I haven't solved this yet. I'll zoom out. What do we have here? A big square. And these triangles are all congruent that I drew. And if we know the triangles, we get the hypotenuse, right? So how do we find the lengths of these triangles, right? Because if we can do p-tag and get the side. Now that's the big question. Now, is that going to lead to success? I don't know.
Do you like find this on the internet?
No. The problem? Yeah. I follow a lot of Twitter pages that have questions like these, yeah. That's why I have Twitter.
Wait, you have Twitter?
Of course I do.
Oh my gosh.
Of course. I'm very online, guys. I'm very online.
You have like burner accounts?
Of course. Right?
Comment on what?
Bernie Sanders 2020. I'm one of those Bernie bros you read about. I'm always like harassing people online.
Yeah, comment on.
Right.
Comment on.
Let's put that away. Good job, guys. Excellent effort today. I really appreciate it. All right, let's finish this up. You are period 3. Where's my period 3 one? It's period 1. Is it in here? I think it's in here.
Travel is triangle work.
I can't find.
No. I hate you, Luke. I hate you. All right. There you go. Hi, Ellie.
Can you spell back
Well, maybe today.
Yes, I'm here. Yep. Yes,
Where/when can
SAC?
right here.
Okay.
I don't do it always, but there's my special bin for all of you guys right now. All right, so yesterday we found out that the angle bisectors make the incenter, and the incenter is the center of a circle that's inscribed in the triangle, meaning that the distance from the center to the sides will all be the same because it's radii, right? And again, we measure things distance-wise at a right angle, right? You wouldn't measure the distance from my head to the ceiling at this angle, right? You'd measure straight up so it hits it at 90. Yes.
So, wait, that center point, we're not,
Yep,
does that
G.
always make a perfect circle?
It does. And the reason for that is when you connect the angle bisectors, the intersection point is always the same distance from every side.
I don't know.
I was looking at the next one, it didn't look like it would make.
Oh, no. This is only when we connect the angle bisectors up,
Oh,
right? And for any triangle, this will hold true, right? We messed around with GeoGebra the other day. We connected our angle bisectors, and the center was always the same distance from every side, which means it makes a perfect circle. And we call it an inscribed circle, scribe meaning right, in meaning inside, right? Written inside the triangle. We also talked about medians. Remember, that's the centroid or the medicenter, whatever you want to call it. I prefer medicenter because it reminds me of medians. It's also the way that I learned it originally because I learned my stuff from YouTube. I'm a real math teacher. That's right. It's the center of mass, right? The balance point. And now we know the balance point on something, even if it's very unbalanced, like this side's weighed down a lot more. The balance point on something will always be on the object, right? It's somewhere on the ruler. If I wanted to balance the ruler, no matter what's sitting on this to make it heavier, the balance point will never be off the ruler, right? That's just not how things work, right? So we shouldn't be surprised that the centroid's always inside the triangle, right? If it's acute, there it is somewhere, right? If it's a right triangle, midpoint to vertex, there it is, right? If it's an obtuse triangle, midpoint to vertex, right? It's always going to be inside. That's the balance point. So we shouldn't be surprised that the centroid's always inside. What about the incenter? When it's an acute triangle, like this one, it appears inside. Without getting GeoGebra out, and Zayden, you can't answer, neither can you, Xavier. Where will it be for a right triangle? And where will it be for an obtuse triangle? Where will the incenter be located? Will it always be inside the triangle? I'm going to tell you right now, there are some centers here that won't always be. Why do you think the incenter will always be inside the triangle? What do you know about it?
You'll be in the angle will be the middle of it, right?
What do you mean? So the angle bisectors, yep, that's what creates G, right?
Like, yeah, I don't know. So, the bottom of those three triangles, is that what you're talking about?
So Luke, let's catch you up. So this is an angle bisector, right? AF, it cuts this angle in half. CE is an angle bisector, BD is an angle bisector. Where they intersect is point G. We said point G is the incenter because it's equidistant from every side. And when we have a point that's, we can draw a line from that point in all directions, equal distance, that creates a circle, right? So what it does is it's the center of a circle that fits perfectly inside the triangle, okay? So will this always be inside the triangle? We said this one definitely is because that's the center of mass, right? And you're never going to find a balance point on an object that's off the object, right? That doesn't make any sense.
Yeah, it has to be inside the triangle, because otherwise it could be equal distances, right?
Maybe, I don't know, maybe there's a point outside the triangle that I can find for a certain triangle that'll be the same distance from all 3 points, or all 3 sides. Will it be inside, outside, on the triangle? What's going to happen?
Where do you want this?
And how do you know?
The top.
Yeah. Right. Think about it. What do we know about the incenter?
It's the center of mass.
Nope, that's the other one.
What? Okay, switch.
Buckets.
It has to make a perfect circle.
It does. And where is the circle located? Where is the circle located for the incenter? Inside the triangle, right? Now, if I'm a circle inside a triangle, will my center ever be outside the triangle? No, right? Here's the circle. It's inside the triangle. Where's the center? Is it over here? No, it's probably, maybe you're really bad at finding the center of a circle, but you're never going to be like, is that the center of the circle? Right? Maybe you're like, is that the center? And I'm like, close enough, right? But if the circle's inside, will the center be inside?
Oh, yes.
Yes, right? So even if it's a right triangle, that circle will still be inside. Even if it's an obtuse triangle, the circle will still be inside. It'll all be the same distance from every side, right? So of course it's always inside. So far we have 2 centers that we've talked about. The center of the angle bisectors, right? That's the incenter. It creates an inscribed circle, right? It's equidistant from every side, so that creates a circle, right? Circle's inside, the center will be inside. Center of mass, the balance point. Well, it better be somewhere on the object I'm trying to balance, right? This would not be a good guess for a balance point, right? Let's talk about orthogonals. They create the orthocenter. So G is called the orthocenter. Like when you go to the orthodontist, right? You go to get your teeth straightened. And so orthogonals are 90 degrees, right? Straight lines. All lines are straight. All right, so this guy creates the orthocenter. Now, this doesn't have a lot of interesting properties, and we will talk about this later. It turns out that this triangle and this triangle will be similar. This triangle and this triangle will be similar. And this triangle and this triangle will be similar. Kind of, yeah, right? Because vertical angles here and here means we have shared angles, right? Right angle, angle there, right? And so therefore they must be similar by double A. Here and here, those are vertical. So we got double A because of the right angle and the green angle. And then here, red angle and right angles. So double A, all those triangles are similar. It's almost like that line right here cuts the triangle in half, and we dilate that triangle, right? We shrink it down and send it across. Right? And this one grows from small to big. Remember dilations, right? They have a dilation factor like times 5 times 4, right? That's what similar triangles do, right? They're times 3 times 2 times half, right? It's a dilation, essentially. Let's look at number 3, perpendicular bisectors. We call G here the circumcenter. So if you go to the orthocenter for orthodontistry, what do you go to the circumcenter for? Circumference. So that's where this is. So be careful how you say this one. Now, it turns out the circumcenter is always the same distance, not from the sides, like the incenter, but from the vertices. So if I'm the same distance from every vertex, what is G the center of? If G is the same distance from every vertex, what's G the center from? The center of? Well, when it's the same distance from the sides, right, we get a circle that's inside, right? When it's the same distance from the vertices, what are we going to get? What are we going to get? Same distance from the vertices. Right? I have a center point, and I've got lines going from it the same distance. I'm going to get a circle. What's the circle going to look like? It's going to be on the outside, right? Does that make sense? Those are all radii. So we've got radii of a circumscribed. Careful how you say that one. Circumscribed circle. Now, we call it circumscribed because circum means to like circumnavigate, right? To go around, to cut around. Yeah, right? And then scribe means to write, right? So circumscribe means to draw a circle. And we're drawing a circle on the outside, whereas an inscribed is drawn inside, right? So it turns out it'll always be the same distance from the vertices. We also know that's made by perpendicular bisectors, so we know these sides represent midpoints, right? These points right here are midpoints of their sides, and they go from there at 90. Now, what do you know about these two triangles here? Triangle ADG and triangle CDG. These two.
Oh, they are congruent.
They're congruent by what?
Side.
ASS? Oh no!
Wait, what? Doesn't that work?
We've got ass.
Doesn't that work? Or HL?
HL, that's right. We got hypotenuse and leg. So these two triangles will be congruent. And these two triangles, whoa, I lost my mind. And what did I just do here? Okay, so these two triangles will be congruent. Right? Here and here. These two triangles will be congruent. And these two triangles will be congruent. That's kind of cool. Again, the main idea is that circumcenter triangle goes all the way around. Orthocenter and the circumcenter, we didn't talk about whether it is on the inside or outside or what for each triangle, right? Those are both acute. So for acute, they're on the inside, right? let's go to GeoGebra, and I will show you where the centers occur.
Love nuts.
So for acute, they are on the inside. That should not be shocking. Let me delete all this. Yeah, shout out to Nelly. Best of luck with that.
When you rename.
All right, so here's our triangle. I want to make, let's do orthocenter. So I need to make orthogonals, right? So I need perpendiculars. I go from a vertex to an opposite side at 90. So that's a 90-degree angle. Everybody see that?
See.
Cool. Vertex to opposite side at 90. Let it fall where it may. Does it always cut it in half? Not necessarily, right? It just drops to 90. This one drops to 90. There's 90 degrees right there. Where they intersect, we call that the orthocenter. Whoops. That's the intersection of the perpendicular bisectors. Now, if I make this a right triangle, what do you think is going to happen to the orthocenter? Think about it. The orthocenter is the intersection of the perpendiculars, right? Think about a right triangle. Where will the intersection of the perpendiculars be?
On the hypotenuse.
Not on the hypotenuse. I don't see any perpendiculars here. Where will the perpendiculars intersect? Where will the 90-degree lines intersect? Draw a 90-degree line from here. That hits the other side at 90. Did it?
At the right.
Draw a 90-degree line from here that hits the other side at 90. Did it? Where are they going to intersect? Here. Now the other one is draw a 90-degree from here that hits the other side at 90. That's that, right? But if two of them intersect, the third one will. So as I make this 90, watch that. Boom. Right in the vertex of the 90-degree angle. Make sense? So it's on the vertex of the 90-degree angle. So for a right triangle, write that down. For orthocenter, acute is inside the triangle. For a right triangle, orthocenter, it'll be on the 90-degree angle, of course, right? Because we've already got two 90-degree lines right there. Okay? Now, using this logic, when we're acute, we're inside. Now watch it. As I get more 90, as I get closer to obtuse, I head this way. So where's it going to be when I get obtuse? It's going to be outside the triangle. Out the back end, right? As I make this bigger, it continues pushing the orthocenter this way. As I get bigger, it pushes the orthocenter out. Don't just write it as outside the triangle. Notice that it comes out the back end, right? It goes through the 90-degree vertex to the outside. What? I didn't hear what you said. Back end meaning this, yes. So it's inside for acute. It's on the right angle for right. So on 90-degree vertex. And for obtuse, it comes out the back end, right? Outside. And notice it comes out through that used to be 90-degree vertex, right? It keeps shooting out. It starts here. It moves here. It keeps heading in that direction. You guys see that? You can imagine the animation heading that way, right? As the triangle opens up. Let's talk about perpendicular bisectors now. All right. Here's our triangles making a cube. Perpendicular bisectors. I need midpoints and perpendicular lines. So I'm going to do this. Midpoint perpendicular. Midpoint, it goes 90 from there. Midpoint, it goes 90 from here.
Where are you?
Midpoint, and it goes 90 from there.
Are you
What?
supposed to be watching?
Are you supposed to be
Oh,
watching it?
sorry. Go back. All right, so here's my triangle. Midpoint, 90 degrees from there. Midpoint of this line, 90 degrees from there. See how it's shooting off 90 here? It doesn't necessarily go through the vertex. It's okay. Midpoint to 90. Where they all intersect, we call that what? What's the intersection of the perpendicular bisectors?
Orthocenter. Wait, circumscribed.
Circumcenter.
Circumcenter.
Place you go to get all of your circumference needs. All right. There we go. Acute is inside. Now remember, this forms a circle because it's the same distance from all of our vertices. So here's the circle. See how it hits all my vertices? Because it's always the same distance from all the vertices. Now, as I change this triangle to a right triangle, watch what happens. Where is it heading? Towards the hypotenuse. And where does it end up? Not just on the hypotenuse, but where on the hypotenuse? The midpoint of the hypotenuse. So what I'm saying is if you draw a 90-degree triangle where all the points are on a circle, the hypotenuse will always be the diameter of the circle, right? You got 2 radii there. It's always the same distance for every point. The distance here is the same as the distance here, as the distance here. Let me color that in. These are all radii. I'll go back to a cube. See how it's all the radii of the circle? Oh no. This is, oh no. Oh dear. Now what's going to happen as I make this triangle right? It gets here, right? Midpoint?
Right.
On the hypotenuse. What happens when I go obtuse? What do you think? Watch where it's heading. Where do you think it's going to go? On the outside. Now, unlike the last one we did, here, let me make this more obtuse. Unlike the last one we did, this one's heading out the front, right, where it opens up wider. And the reason for that is in order to make a circle with these 3 points, right, I have to go really wide. So it pushes it out this way. So of course it'll end up outside when it's obtuse, right? In order to make a circle, I have to go really wide to hit them all. So if we go back real quick before you go, do not leave when the bell rings. You're going to want to write this down. Acute inside. And the reason for that is because we have a circle that goes around like this, right? Right triangle. It's on the midpoint because we have a circle that goes like this. And that's the diameter, right? Cool. And then lastly, obtuse triangle. Well, in order to even connect all those points, I have to do a really wide circle, right? And notice it's not out the back, it's out the front. All right, get going. I'll see you tomorrow. We'll review. This is your quiz, basically, guys. Tomorrow we're going to apply this just a little bit. But in general, that's the quiz.
Can I review the tests?
Ideally, yes. I'll be here. Yeah. Right, you on it? Yeah. See you later. Nice job today. Good warm up.